Okay, I think I have started recording now. Okay. So how is everyone, and do you have any questions? So no questions. Shall we start? So let's do a quick recap of what we did the last class. We did two sort of basic things. We wrote down the formalism for two species dynamics. Okay. So we write down equations in the following way, right? If the two species numbers are denoted by n1 and n2, we can write this as, so the growth rate of species 1 depends on the abundance of both 1 and 2. Likewise, the growth rate of 2 depends on the abundance of both 1 and 2. Okay. And these f1 and f2 are the growth functions. They need not be same because 1 and 2 grow differently. Okay, and then we can sort of carry forward the notion of equilibrium. And when we learn a bit more, we realize that there will be many other types of dynamics possible in two species. But the idea of equilibrium continues to hold true, and that happens when both n1 and n2 do not change. Okay, and we obtain those equilibrium values by simultaneously solving for the equilibrium values of n1 and n2 by setting both the growth functions to 0. Okay, and then we can look for stability. We can analyze the stability by looking at what's called the Jacobian matrix J, whose ijth element are basically given by you take the so species I, it could be 1 or 2 in this specific case, and you take the species J, their abundance, and you calculate this partial derivative, and from that you get a matrix J, and you compute this matrix element Jij by the partial derivative of Fi with respect to Nj, and then you look at the eigenvalues of the matrix J. Of the matrix, Jacobian matrix J. And then if the real values of all, if the real part of all the eigenvalues, the real part of all the eigenvalues are less than 0, then you have a stable equilibrium. Okay, so another way to state this is find the eigenvalue with the maximum real value, and if the highest eigenvalue, the highest of the real values of the eigenvalues is greater less than 0, then it must be in a stable equilibrium. Okay, that's the sort of basic mathematical formalism, and then we also discussed how to analyze this graphically. The basic idea is we draw null clines. So for example, null clines for species 1, we sort of find that by setting n1 dot is equal to 0, and we may get 1, 2, or many many null clines, and then again you do this for species 2. Okay, and the intersection of null clines null clients, that will give you they will correspond to equilibrium values. And then you can look at the stability by, by looking at the signs of n1 dot and n2 dot around these equilibrium values, and then conclude if they're stable equilibrium or unstable equilibrium, and so on. Okay, so this is a sort of broad, mathematical formalism. Any questions on this for two species? Any questions? No. If there are no questions, I will summarize what we learned from the two species competition model. Okay, and in fact, the model we studied is called Volterra competition model, where basically we wrote down the species one dynamics as follows. Okay, denominator will be K1. K1 is the carrying capacity of species one. The basic assumption we made was, in the absence of species two, the species one grows logistically at an intrinsic growth rate R1, and then reaches a carrying capacity K1. Okay, so K1 is the carrying capacity. Okay, and then K1 minus N1, the first term here minus N1, captures the intra-specific competition. And then alpha 2, 1 and 2 captures the effect of competition of species 2 on species 1. Okay, so alpha 2, 1 is the, you can say, sort of, some coefficient that captures the strength of competition of species 2 on species 1, and N2 is the species 2 abundance. Okay. Likewise, we assume that species 2 also reaches a carrying capacity K2 in the absence of species 1. However, because of competition between 1 and 2, it has an additional negative growth rate. So exactly like the previous term, so alpha 1, 2, N1 captures the effect of competition on species 2. So this is also called intra. So you can think of, the first term here. Okay, so there are two terms here, right? Okay, I'm sorry, I made a mistake here. This is N2. Okay. So this term captures basically the intra-specific competition, and this term captures interspecific competition, right? Maybe I should use different colors. So this is whereas this is interspecific competition. Okay, so so just let us think about this intuitively. Okay, so what we can, so we actually found that there are 4 possible cases here. Let's just summarize all the 4 cases today. And we just were drawing null clients. By drawing null clients, looking at the intersections and the flow of the population, we were able to make conclusions about how species reach equilibrium, what equilibrium are stable, and so on. So somebody has a question, or if you have a question.
Hello.
Yes.
Yes, sir. So I had like a question, like you've given like a strength term like alpha 2 and alpha 1, 2, right? For the other species. What about like strength term for intraspecific? Like why is it assumed to be 1?
So you can see the thing is whenever there are two strengths, you can always normalize one of them, right? So whenever there are two parameter values, you can assume that the first one is 1 and relative to that you compute the other one. Does it make sense? So imagine a case where alpha 1 is greater than 1. What does that mean? That actually means that the intraspecific computation is more than the interspecific computation. Interspecific computation is more than the strength of intraspecific, right? So intraspecific is taken to be 1 unit here, okay? And interspecific is taken as alpha 2, 1.
And I had one more.
Okay, does that make sense? So I could have written another coefficient, but as you know from dimensional analysis, you can always reduce one parameter whenever there are two comparable parameters of the same units. That's the basic idea here.
Yes, sir. And I had one more question. Like
I can't hear any other questions.
Hello.
Harashi, I can't. Your voice is now suddenly down.
Hello.
Yeah, now I can hear. Yes.
Yes, sir. So in this you mentioned that.
No, I can't hear again.
So we are assuming. One sec, I'll type it. Am I audible now?
Now you're audible. Suddenly it sort of oscillates.
Yes, sir. I'll type it in the chat box. I'm not sure if I'm audible.
No, now you are audible, but the moment you're asking question, then it goes away. See, for those of you who find the intra and inter slightly confusing, you can always think of within species and between species. Intra is within species, inter would be between species. Any other questions in the meantime?
Also, in the last class, you took K1 as a intra-specific computation parameter.
That's We'll come to that. Yeah, I understood that confusion. Yeah, but we'll come back to that.
Okay.
So they distinguish the two. What is the per capita strength of competition? What is the population level strength of competition? Okay, so the simplest answer is per capita strength is 1 unit, and alpha 2, 1 and alpha 1, 2 respectively for all the three types of competition. Okay, but if you think of the entire population level consequence, you multiply it by the population size, right? Okay, that's why it becomes K1 and alpha 2, 1, K2. Okay, does that make sense?
Okay.
Yeah, Rashi, did you write? Okay, I'll check now. Okay, yeah, in case of this model, if alpha 1, 2 is very high, it won't be sort of like predation that one species overpowering the other. No, predation and competition are fundamentally different interactions in ecology. Predation is you just consume the other individual directly, right? Whereas in competition, and the competition is also mutual, right? Both of them affect each other. Whereas in predation, one only affects the other, not the other way around. It's an asymmetric interaction. Okay, competition happens because they are both. There is an invisible factor that we haven't written in this model today. They are both wanting same resource, which is why competition happens. Predation happens for a very different process, right? One wants the other. For one, two is the resource. That's the predation. But here, both 1 and 2 want the same resource from R.
Yes, sir.
It's useful to distinguish that. I mean, maybe in some mathematical limit, you can assume that they are, I can convert competition to predation, but, I don't think process-wise, they are very fundamentally different. Okay. Okay, so now let's just think of all the 4 cases that we discussed last time. So now, if you remember how to compute the net effect of competition. So as we said, 1 unit and alpha 2 1 is the per capita influence. Now, if you think of net effect, okay, so let's look, think of species 1 now. For species 1, K1 is the sort of, when you have a species 1 at its carrying capacity, K1 is the total effect of intraspecific competition. Okay. Whereas alpha 2 1 K2, right? That will be the the total effect of the competition. Okay, so because of species 2. Okay, what does this mean now? This is the effect of competition on species 1 by 2. This is the intraspecific competition for species 1. Okay, so let's just write this down. Total. This is the interpretation that Amir offered, and I sort of liked it. Okay, total. It's not. I think Tarun Menon, if I'm right. Sorry, intraspecific competition for species 1. This one is, again, if I were to stick to the colors, this would be total interspecific competition by SP2 on SP1. So what this means is the intraspecific competition is now higher. Competition because of other species is low. That's the sort of case of species 1. We can now choose 2 possibilities for species 2. Okay, which would be, for example, K2. So I don't know what all I called last time as case 1, case 2, case 3. 3 cases. I will just be consistent with it, so that I won't change cases. Okay. Okay, so case 1 is species 1 excludes species 2. Okay. Okay, now for species 1 with internal competition is more, whereas for species 2, external competition from other species is more. If this happens, what happens? What should happen?
The other. Species 1.
Species 1 competitively excludes species 2. Does that make sense to everyone? Okay, now an alternative way of thinking about this is as follows. Okay, now how do we, for example, the same cases, how do we think about these 2 conditions? Entirely different. So consider the scenario, okay, when let's think of species 1 perspective. Okay, what is the species 1 perspective? What is the worst scenario for species 1? The system currently has only species 2. Okay, let's consider that extreme. In such a case, if you introduce a small amount of species 1, what do you think will happen? So what's the total competition felt by species 1 now? It will be this term, right? Alpha 2 1 K2. Is that right? It will be this term that will be felt by species 1. N1 is very small anyway. This, let's assume, is negligible. So the growth rate of species 1 depends on K1 minus alpha 2 1 N2. When you have, so imagine a scenario where only species 2 is present at its carrying capacity. I have introduced a small number of species 1 now. So N1 will be very small, but this is now alpha 2 1 K2. If K1 is greater than alpha 2 1 K2, that means the growth rate of 1 is still positive. That means a small number of individuals of species 1 can invade species 2 at its carrying capacity. Okay, therefore, and exactly the opposite happens when system is full of species 1. When the system is full of species 1, the competition effect on species 2 will be alpha 1 to k1. But because k2 is less than this, species 2 cannot invade that system. So which means that species 1 will exclude species 2. Okay. Any questions on this? Because please understand this, because this is the sort of most fundamental sort of once you understand this, everything you can write down all the 4 conditions, just thinking through what all of these coefficients mean. Okay, maybe even let's write down another interpretation of this equation, which is I don't know what, let me read. So this condition means that species 1 can invade species 2 at its carrying capacity. I think this is sufficient to say, no? Can invade species 2 sufficient, right? Because we do invasibility analysis only when the other one is fully occupied anyway. Can invade sp2. And what does this mean? Species 2 cannot invade species 1. So this is the interpretation I initially began explaining when I explained each of the scenarios. Okay, so we can likewise write case 2, which is converse of the above, right? Okay, which will lead to k1 less than alpha 21 k2 and k2 greater than alpha 1 2 k1. What would that lead to? Species 2 competitively excludes species 1. Okay. Now we have a case 3. Consider a case 3 where neither of them can invade the other. What does that mean? Both of them are less. Okay. Which means k1 is less than alpha 21 k2. k2 is less than alpha 1 to k1. Neither can invade the other, which means that what we have a founder effect. So the initial founding population size determines the outcome. So if initial population of n1 species 1 is higher, so exactly by how much and all will depend on all these parameter values, but there is some separation between the two. Okay, so depending on the population size, one of them will now win. Okay, now we have a case 4, which is exactly the conditions of this will be entirely inverted, right? K1 is so both of them can invade now. Okay, both can invade. What does that mean? So if I start with K1, if I start with species 2 at its carrying capacity, species 1 can invade. Conversely, if I start species 1 at K1, species 2 can invade. So this leads to what we call coexistence. Okay, any questions now?
Sir, wouldn't that be K1 greater than alpha 21?
Yes, I have just gotten the signs wrong, right? The order wrong. Yeah, thank you. This is alpha 21. Is that right? Thank you. Is it fine? Anything else? Does it make sense? All the conditions make sense to you intuitively? Okay, now let's understand coexistence condition a bit better. So what was that? Both can invade, right? That means that K1 was greater than alpha 2, 1, K2. Let's look at the ratio. What does that mean in terms of ratio? K1 by K2 is greater than alpha 2, 1. Is that right? And the other condition was K2 was greater than alpha 1 to K1. So in terms of the ratio again, K1 by K2 is less than, right, 1 over alpha 1, 2. Is that right? So let me write that now in the center here. K1 by K2 is greater than alpha 2, 1, but is less than 1 over alpha 1, 2. Is it fine? Okay, so then now let's think about what do alphas mean, right? One way to think about, as we discussed, was alphas represent relative to intra-specific competition. What is the inter-specific competition, right? So relative to the within species competition, how big or how small is the between species competition? Okay, so consider a scenario. Okay, let's consider some couple of simple scenarios here. So consider a scenario. There are the two species rely on, two species are, let's say, generalists. Okay, do you understand the meaning of generalists? And rely little on common resource. Now, in this scenario, what do you think these alphas will be?
Will be high.
Alpha will be high. They rely little on common resource. When they rely on common resource, little on common resource, do you think the competition will be high or low?
Low.
Competition
It should be
will
low. It will be
This
low.
means low competition, right? The competition is low. Will alphas be large or small? Alphas will be small, right?
Yeah.
So let's randomly assume that alpha 1, 2 is 0.2. And also that, alpha 2, 1 is maybe 0.25. Is that fine? I'm just making up some numbers here. Huh? Okay. So for everybody's with me. Okay. So what will be the, so we have this condition where alpha 1, 2 is 0.2, which means what's the inverse of it? It's 5, right? Therefore, for coexistence to happen, 5, this ratio, oh, sorry. Usually you will write the opposite. No, I have written. No. Let me just invert the entire order. It's so awkward. Sorry. Okay. So the left-hand side, I will write the smaller number. Is that fine? Okay. Let's consider, this is when the coexistence is possible, meaning the ratio of the carrying capacity of the two species must be between 0.25 and 0.5. Now let's consider scenario 2. two species rely heavily on the same resource. So now can you come up with some reasonable numbers for alpha 1, 2 and alpha 2, 1? Five. Why 5? Just think about what does it mean to say it's 5. It means that to get the same resource, I have to fight more with species 2 than with my own species. Does that make sense?
Yes.
Huh? Is it? See, what does any of the alphas greater than 1 even mean? It means that I actually am sharing a resource more commonly with another species than with my own species, right? So don't you think that in some sense alpha is equal to 1 is the sort of, of course, what you're saying is in principle possible, I will eat different from my own species. I don't know what that exactly means. Maybe it's possible in some scenarios. I don't know. Maybe ecologists here who know better than me can explain that. But is it reasonable to say that alpha equal to 1 is pretty much the limit for a large number of cases? Which basically means the other species and I are basically identical in terms of our resource consumption.
It is a reasonable assumption, but also if you think about your own availability depends upon your population. If that's
Size.
the case, then alpha can be bigger than 1. So we are saying like the per capita survivability like doesn't reduce much if your own because of intra-specific competition.
Okay, but yeah, I mean, I guess there might be some scenarios where what you're saying is true. But let's maybe that the one individual of the other species takes so much of your resource, okay, that that has a much more impact on you than your own type. That's feasible, okay. That can potentially happen, yeah. Okay, but let's consider the scenario where let's say alpha 1 is the ceiling for for the time being, and then we can think of the scenario you have also said. So what would alphas be now? 2 alphas be now? What are the reasonable? Some large numbers, right? Let's say 0.9 and let's say 0.95, some arbitrary numbers. Okay. Now let's write down the same condition. Okay, so K1 by K2 must be greater than alpha 2,1. It must be greater than 0.95, but it must be less than 1 over 0.9. How much is 1 over 0.9? It's about 1.1. Is that correct? No, 1.1111. Okay. So now compare scenario 1 and 2. What can you conclude from scenario 1 and 2?
The range is higher.
The range for coexistence is much higher for scenario 1, right? Is that right? So this we can say is high competition. Okay. So now that means the range for, what does the range here is higher mean in terms of feasibility of coexistence?
There is more chance for less vigorously competing species to coexist than more vigorously competing.
Yeah, so which means that species are more likely to coexist in scenario 1, right? What that also means is that, if two species are competing or are competing for the same resource, and if they're if they rely on very similar type, even the smallest differences in their sort of nature will lead to one excluding the other. So basically in scenario 1, which basically means that similar species are less likely to coexist. It seems a bit counterintuitive, by the way. I'm not saying the same species, I'm not saying the identical type of species, okay? But similar species are less likely to coexist, okay? And this is also basically called competitive exclusion principle, okay? So this is a very important principle in ecology, because this sort of raises a very important question. If similar species are very less likely to coexist, so what makes the existence of such huge biodiversity possible, right? So one obvious hypothesis is, just invert this. Most species are very dissimilar.
Like similar species are more likely to coexist than two random species, which might have different carrying capacity.
Similar species are more likely to say that again, sorry.
So here K1 and K2, we need the ratio to be approximately 1.
Yeah.
So isn't it the other way, like similar species are more likely to coexist, which have similar carrying capacity?
Yeah, I mean, so basically, if you think, why, but the smallest deviation from this will also make them not coexist, right? So the region of parameter space that allows them to coexist is much smaller in this case compared to this case.
Okay.
So the ecological regimes over which they can coexist.
Okay. So you mean similar species here implies high competition then?
Similar species will mean, they are using the same, that's the way I'm defining here. Or you can think of the following, if two species are relying, exactly what I wrote in the beginning here, relies heavily on the same resource, there will be high competition, therefore less likely chances of coexistence.
Yeah, understood, thanks.
Okay.
Saying similar species, you're referring to like the alpha values or the K values?
So why do you, this is a good question. Why are we saying they're similar species, right? When we say similar species, why are, in terms of the resource consumption. So they are identical species in some sense. They're identical if the effect they have is, in terms of competition is 1 unit, right? Okay. The farther you are from 1 unit, the less similar you are.
Wait, so there you're checking like the alpha values, right? Or are
exactly. Alpha values tell me alphas being closer means they are very similar.
But then, like, if I look at like the scenario 1, you've taken 0.2 and 0.25, and for scenario 2, you've taken 0.9 and 0.95. So there's like a difference of 0.05 in both the alpha values in case 1 and case 2. But here we are supposed to be looking at K1 by K2 also, right? To conclude the similarity.
So the first thing you should check is, how alpha is close to 1, right? Because that tells you how intra-specific competition and interspecific competition are compared, right? See, alpha is very far away from 1 already means that when they are competing for the same resource, they have less effect on one another.
Okay, yeah, I understood. Thank you.
So don't compare the alphas directly with one another. You must compare alpha with 1 unit, because that's the baseline unit for how they're influencing each other within the same species. So now that's your baseline comparison.
Can it also be interpreted as
So Sean, I can't hear you, sorry. Your voice is not clear. You can try speaking and then I can tell you.
Hello?
Yeah, that's better now. Yes.
Yeah. So I was thinking, can it be interpreted as coexistence is more likely when intraspecific competition is far greater than interspecific competition? So in scenario 1, for instance.
Here the intraspecific is more. Exactly. Yeah, absolutely. Yeah. Low. When I say low competition, I actually meant low intraspecific. That's low. Yeah.
Hello?
Yeah. I know.
Hello?
Yes, I can hear you.
Yes, sir. So your voice actually cutting off. My net is quite bad. Could you repeat the explanation which you gave for why semi-species should look at it from alpha?
So basically, now how do you define similarity? Is one you can ask that question. Do you define similarity by K1 ratios, case ratios, or do you define by the effect they have on each other? So if you define, so I'm going to define similarity based on the effect they have each other in consuming a given resource. Okay. So with that definition, right? The effect they have on each other within the species is 1 unit, right? Whereas the effect they have on each other between species is alphas, alpha 1 to and alpha 2 1. So if alphas are closer to 1, that means the effect they have within species becomes similar to what they have between species. I hope you were able to hear clearly this time.
Okay. Yes, sir. Yes, sir.
Okay. So, in what we have done so far, we have actually hidden the resource. That actually causes a lot of confusion. Okay. Because resources are not explicitly written down in these equations, how exactly are these guys, the resources playing a role is a bit mystery here, right? Okay, so let's do the following now. Let's actually incorporate resource and how species are consuming the resource. Okay, so to do that, there are class of models called consumer resource models. And what they do is basically explicitly incorporate the resource and the consumers. Okay, so let R be the resource. The rate of change of resource. There are many ways of writing this. I'm going to write in a way that unfortunately you may not easily find in books. Let's say capital I represents the input rate of resource. Okay, and then there is some consumption. Consumption rate of resources by a consumer C. Okay, so C is the consumer. And because of the consumption, let's say gamma is the efficiency of conversion. Of the resource, and then gamma is the conversion rate of the conversion rate or the conversion efficiency of this consumption, and therefore C's will increase because of that. However, there are also, let's assume there's a natural mortality of the consumers, which we write as delta times C. Okay. So we have explicitly accounted for resources and the consumers. Okay. So now let's try to see what should this consumption rate be. Let's call that some function f. Okay.
What is I?
I is the input rate. Okay. So there are many ways to think about this system. So for example, imagine I have a chemostat. All of you have heard of chemostat maybe at some stage. So chemostat is a sort of, sort of a controlled environmental condition where you, where there is a constant input of resources, and then there is also a flow. So I'm sort of ignoring the flow part here, because adding, there's also a natural decay rate of resources. Adding that doesn't actually give us any new insights in what we are doing today. So I'm going to ignore that part. Okay. Or you can think of I as the rainfall if you are thinking of a natural environment. Okay.
And can you also define gamma again?
So gamma is the conversion efficiency. For example, if you were to think of this as a food web, right? So gamma is the efficiency of conversion of energy consumed by the consumers. So for example, you may have read in your high school books, it's about 10%, right? So gamma is that number that captures the conversion. Okay, so F is, let's say F is the consumption rate function. What will this depend on? This should depend on both R and C. Do you agree? Okay, so the amount of resources available as well as the number of consumers. Okay, so let's say that resources, as the consumers increase, will this consumption rate keep on increasing? Right, so as consumers increase, so F, if I were to write F as a function of C, do you think this will be an increasing function, or this will be a decreasing function? This will be some other function. What's the most reasonable assumption?
Right.
It's an increasing function, right? Okay. On the other hand, if I were to write F as a function of R, what will that be?
Decreasing.
Decreasing. As resources increase, the consumption will reduce. Increasing or decreasing? So it is an increasing function. This is basically like the harvesting function, by the way. What was the most reasonable assumption for harvesting function? Will it keep on increasing forever as resources increase? It also saturates. Okay. So basically an increasing function with respect to C and a saturating function with respect to R. Okay. So we can write it in the following way: R divided by R0 plus R times C. Is that fine? And let's assume there is a coefficient beta. Okay. Should we now write down the resulting model now? Resulting consumer resource model, dr by dt is I minus beta C R divided by R0 plus C, R0 plus R, whereas dC by dt is gamma beta C R by R0 plus R minus delta of C. So this is a fairly simple consumer resource model. There are many variants of this. For example, you can assume that the R, in the absence of, so let's think of what's happening here, right? If the consumers were not present, what happens to R? R will keep on increasing at a rate I. So that's slightly artificial, but one can add a depth term for R to sort of avoid that. But as I said, it doesn't really add a whole huge sort of value to what we are doing today. So I'm going to avoid that.
Sir?
Yeah.
With respect to like the second plot that you drew, FR plot, in that you're assuming that the number of consumers are constant, right? While you're drawing this plot.
For a given, you can say that you can think of that as for a given value of C, how should this function look like? Right, just like the previous one, right? When we wrote F as a function of C, we assumed R for a given value of R. Okay, so this is like a given value of C. So I'm not assuming that C is constant per se. This is like equivalent of looking at partial derivatives. When you do partial derivative, you assume that the other is constant. Look at the derivative. So here I'm assuming that The other value, other parameter, other variable is constant. I'm just looking at the function directly.
And why are we not taking like the sigmoidal equation for this?
For the first one?
No, for the second one, the FR.
We can take, there's really no harm, but I'm just keeping it a bit simpler. Mathematically, this is simpler to analyze. But we can do the sigmoidal also, R square, yes, we can do that.
So what is DC over DT in this case? Is it the population size of the consumer?
Absolutely, yeah. So C is the consumer population size, right? So R is the, so what is R? And again, let's write down here. R basically is the amount of resources and C is the population size of consumers.
Shouldn't it be delta C, then not like the dash?
What dash?
Like in the DC by dt, it should be delta C, right? Not the the other C that you've drawn.
Oh, delta is a coefficient here. Just a so delta.
Yeah, that's like the dead term, right? It should depend on the
per capita death rate of consumers. Is that fine?
Yeah, but I think you multiplied it with the consumption rate here in the equation.
C is not the consumption rate. C is the number of consumers.
Okay.
So population size of consumers. So are you now, do you feel comfortable with this kind of equations now? Okay. So is this fine? Shall I go forward? So now we need to understand this, right? So let's again do the standard stuff. What are the equilibrium? How do you find equilibrium? You set both R dot and C dot to 0, right? Simultaneously. So what do you find when you first set the first equation to 0? There are two terms, basically they have to be equal. When I is equal to BC R divided by R star R0 plus R. Okay, so that gives me the condition BC star R star divided by R0 plus R star is equal to I. Okay, that's the first condition. If R star and C star are the equilibrium values, then they must satisfy this. Okay, which means the input rate of resources must be equal to consumption rate by the resources, right? Okay, that's the first thing. I've just inverted the order, but that doesn't matter. Okay, the second thing is this entire thing must be 0, the right hand side of the second equation. When you write that, I can write that in the following way. Is that right? So I have taken C as a common factor, C star is the common factor, which means that only one of them need to be 0. So this could be 0 or this could be 0, right? So what that means is that C star is equal to 0 is one possibility. Or
the gamma beta should also come in the denominator, right?
Denominator. Where, sorry?
Where delta divided
by
right.
Gamma. Oh, I'm so sorry. I messed up. They shouldn't, I shouldn't be taking them out at all. This is gamma beta. Thank you. So one possibility is C star is equal to 0. That's when the second equation can be 0. Alternatively, you can have this term to be 0, which is so gamma beta R star divided by R, there's no R0 star, there is just R0 plus R star is equal to delta. So I'm going to write that as R star divided by R0 plus R star is equal to delta by gamma beta. Is that fine? Okay. Is everyone fine so far? Is that correct? Okay, so here is the thing. So this condition number 1 has to be always true, because that's the only way the first equation can be 0, right? That's the only way to achieve R dot is equal to 0. C dot is equal to 0 can be achieved by one of these, either of these two. So let's consider this possibility, which means there are no consumers at all. Okay, if there are no consumers at all, what happens to condition 1? This implies, that's so, yeah, right, that's exactly, so it means I is equal to 0. That means C star is equal to 0. Is it feasible in general? If I is non-zero, is this feasible? So this necessarily implies that I is equal to 0, right? Which means that equation 1 is not always satisfied. So therefore, this solution is basically ruled out as a general solution. Do you agree with this?
But generally speaking, like you can say that there's no consumers, and yet, I mean, resources can just, I mean, be present, right? Like ecologically speaking.
I see your point. I see your point. But that will not be an equilibrium. I mean, what you're saying is a feasible scenario, but since we're looking at the equilibrium solutions, that's not an equilibrium solution. Do you agree? I hope you understand the difference between the two, right?
Okay, so you're saying it'll just keep on increasing.
Yeah,
okay.
So there's an equilibrium in terms of R. So imagine I had put in the first equation minus some D times R, a death rate of R, that would still have been a feasibility. Okay, so in some sense, this model is slightly unrealistic. Okay, but let's explore, within the realm of this model. Okay. Okay, so which means that the equation 1 necessarily has to go with equation 2, which I have just written down here. So the equilibrium solutions for this is are basically equation 1 and 2 combined with one another. Okay. Okay, so now what are the equilibrium solutions now? Okay, why is this jumping suddenly? Okay, so let's go back, and we need to eventually know what is R star and C star, right? So since R star divided by R0 plus R star is delta by gamma beta, I can replace that in equation 1. I can substitute equation 2. Substitute equation 2 in 1 to get C star to be equal to, okay, beta cancels out, okay, and so correct me if I'm wrong, I gamma by beta. So this is the equilibrium.
By delta.
Oh, thank you. Okay. So this is the equilibrium, so value of consumers, which is basically input rate of resources times the conversion efficiency divided by the death rate of C. It makes intuitive sense, right? So whatever the input is converted to at some efficiency gamma, and then you divide by the death rate. Okay, that will give you the equilibrium value of C. And likewise, you can find equilibrium value of R by just substituting solving the equation 2 Okay, so can somebody, I mean, I hope you can do this yourself. I'm not going to, I haven't done this, so I don't have it written up right away here, but this is the equilibrium. Is that fine? So can you, so that we have found that there is only one possible equilibrium solution, and that's given by equation 2 and equation 3. Now, if there is only one possible equilibrium, will that be stable or unstable?
Stable.
Why? Let me give you a counter example. Let's consider this dy by dt is equal to alpha y, where alpha is greater than 0. So what is the equilibrium?
Unstable.
Y is 0, but is it stable?
No.
No. So it's not guaranteed to be stable, but intuitively you can guess here in this case that it has to be stable, right? So primarily because, you can't have, with some input rate of resources, consumers will reach some, some stable state, okay? Some, some equilibrium value, okay? So it makes sort of intuitive sense. You can sort of formally verify that by drawing null lines, okay? So let me quickly do that here. R and C. Okay, now what are the null lines for what is when does R dot become 0? Only when equation 1 is true, right? Which so it's actually a slightly C times R by this is a constant, so it requires some effort to plot that. Okay, so I think you can use a software to plot. And when is equation, and the another null line is equation number 2, which is this hyperbolic equation is basically delta is a constant. Okay, so if you plot these two, you will find an intersection point, and you should be able to find, whether it is stable or not. So I'm not going to do that because I will probably get this wrong if I try to do it now. Okay, but you should be able to do it. Okay, so that's because since I haven't done, and we need to have a lab assignment now. This is your first lab assignment today. Draw null lines and find equilibrium and stability. Okay, that's your first lab assignment today. The next one, which is really the more interesting one, is yes. So I will write down both of them today. Just in fact, I would like you to focus more on the second part, because the first part is fairly sort of routine stuff. Is check equilibrium and stability for resource consumer model. The B, which is the one, is generalize our C model to incorporate two consumer species. Okay, find equilibrium or equilibria rather, and stability, right? Interpretation. Let me add an important point here, which is keep it to be a single resource again. Okay, but add one more consumer species. Is that clear to everyone?
And between the two consumers, there'll be competition, right?
That's a very, very good question. So how will the competition, how would you incorporate competition between two species now?
So that will be inherent, right?
Exactly. So you should not write another low-Cavalterra model between. So you call them, as a, so basically you have R, C1 and C2, okay? There's the three, entities here now, right? So the key thing you must make sure, C1 depends on R, C2 also depends on R. So the interaction between them happens only because of R. Okay. So you don't have to explicitly write how C1 and C2 fight. In Lotka-Volterra model, you did that because you did not have an explicit R there. Okay. Does it make sense? So by the way, I don't know how many, so if you will also notice one interesting thing, if you actually simplify this model, this basically has all the features of a single species logistic model. Okay. So likewise, what you will find technically here is that this will have features of Lotka-Volterra competition model, but under the condition that both species depend on the resource R. Okay. So I would like you to basically write the three equations now. What's the equation for R dot? C1 dot and C2 dot. Is that fine? Any questions?
And how do we determine that what is the level of like dependence? Like as you said in the previous model, they heavily depend on the same.
See, this is the only resource available in their ecosystem. R is the only resource available. Both of them depend on it.
Okay.
That's why I said only one resource. There's only one resource.
There is a high competition between the two.
Which necessarily means that it's only, so this model that you're going to do now is will only capture high competition scenarios.
Okay.
So what do you think will be the result, by the way? Can you guess the result?
There won't be any coexistence then because the range is very short as we derived earlier.
Yeah. So yeah, but yes, but there will be a line of coexistence, but it will be extremely narrow. How narrow will it be? Can you make a guess of how narrow in terms of parameter space will that be? Okay, that's what you will find out. Okay.
And one more thing, in the previous page, while writing C dot is equals to 0. So there we have a C star is equals to 0, and there is no term of C in the other equation.
Which equation, sorry?
The second.
This part has no C at all, right? Yeah, that's right. Yeah.
So when we draw null kind, so we should have a relation between two variables, right?
Well, that's right. Do it. You should be able to do it. Yeah, that's a good point. Yeah. But there is a relationship between. So what is interesting here is the null line of species 2 depends. There are basically two null lines. One is C star is equal to 0. So maybe I can just do it for you right away. So species 2, let me write with red. C star is equal to 0. How does it look like? Like this, right? This is one null line. Sorry for such a horrible drawing. Sorry. Okay. So the one null line is this. What's the other null line? It is this. So there is no C dependency here, right? What does this mean? It's basically R is basically here. So R is basically, just forget R star here. It's basically R. So if you solve this, what do you get? R is equal to some dependence on gamma, beta, and delta, right? So basically R is a constant. So is it a positive constant or negative constant? So another one will be another constant. R will be a constant. It will be something like this.
Okay, yes.
That's the second null line of species one. On species one has only one null line, right? So BR divided by R0 plus R is constant. So that has a functional form, right? Yes. I think it will be some kind of this kind of a function. So, but write that with a blue line. So we'll get something like this. No, I won't write that. So there'll be some intersection point. I mean, I could be wrong. So so write. You should be able to do this yourself. Okay. Yeah. And of course, null lines becomes even more difficult when you have three species. So you have to use a combination of geometric intuition and algebra here to come up with answers for the stability equilibrium. So don't worry about the first part at all right now. Do the second part because I want to see how you're all doing that. Okay, so I'll open the breakout rooms now. I will share, open the sharing preference. Oh, I'll stop sharing. Now I can. Multiple participants can share.
I have a doubt. Like you explain that alpha, the value.
Yeah. Hey, I can't hear you in the live well.
Alpha 1, 2 and alpha 2, 1. Hello, sir? Hello? So
yeah, now
remember
I can hear
you explained that alpha, you explained that alpha 1, 2 and alpha 2, 1 should be less than 1, right?
So it doesn't have to be, it can be different. It's, for example, if alpha 2, 1.
But you gave the reason, right? Could you repeat?
So I basically said that.
So I was asking, could you repeat what you said?
So see, imagine there are two bird species. They are all, let's say bird 1 depends on, nuts and insects. Okay. And bird 2 depends on nuts and fruits. Okay. So there's some overlap of nuts here for both of them. Okay.
Correct.
So now, so intra-specific competition, that the same guys will, will eat both nuts and, the species 1 will have the same sort of, overlap, and the other one. So the overlapping part is here, the nuts, right? So now imagine a scenario where their secondary diet is gone. So nuts are the only ones available, right? Okay. So within themselves, they are competing for the nuts in the same way as they did before.
Yes.
Right. Now they're also competing for other species.
The food resources in common with two individuals of the same species. Okay.
So unfortunately,
better now.
Sorry, I can't hear you. Sorry. You said it's better. Hi, is it okay?
I said I understood it now, sir.
Okay, great. Thanks. I think everyone is there. Let's just discuss a few points that I thought of, wanted to emphasize. The first point is, I think most of you have gotten the writing of the model on the right lines. Okay. So there will be two steps involved in the next thing, which is, what are the equilibrium, what is the stability analysis, and what's the interpretation, right? So so pay attention to finding the equilibrium carefully. Okay. So don't worry too much about the stability analysis part. Just use your intuition, like we did for the previous case. When you have a non-zero input rate, R will increase, that will lead to some C, right? So therefore, the C non-zero equilibrium is stable, is something we can conclude reasonably, right? So I don't expect that the stability analysis you will do using Jacobian matrix. Don't waste time on that, please. That's going to take, it will drain massive amount of your time. Please don't do that. So just do entirely intuitive argument. But what is the interesting point I wanted to focus on? What are the equilibrium solutions for this? Okay, and the existence of equilibrium itself will tell you something interesting. Okay, that's what I wanted to focus on. So don't worry about the stability at all in this case. Okay, is it fine?
We had another question.
Yeah,
what
sure.
Is R0 in this model, in the model that consumer research model?
So R0 is basically like in any of the model where we write down this form of R by R0 plus R, in the harvesting model, we had equivalently, or whatever, X divided by X0 plus X, right? So in all these cases, basically these R0 or X0 in the denominator means the value of the population or the resource density at which that function is half maximum. Does that make sense?
Yes.
Right. So this is also called the half saturation constant. And that is exactly same here. So what's basically, it's the value of the resource at which the growth rate contributed by resource will be half maximum.
So will it change from consumer to consumer?
What do you think?
Yeah, I think so.
It can change. There's no reason for them to be same. Right? Yeah. That I noticed that in a lot of the groups they had taken that to be same across two species, but keeping them different will be good. Okay, but you can also consider see if they were actually same, what will you find? You will find that something very interesting happens. But but you can actually keep them different for more gentle case. Okay, so what you need to basically argue is the existence of equilibrium and the conditions for it. Stability sort of naturally follows. Okay, so you don't worry too much about the stability. So this model for it basically does not admit multiple stable states. So whenever you don't have multiple stable states, the stability is actually relatively easy to resolve. It's either stable or unstable. You can just use intuition to argue whether it has to be stable or unstable. Is that fine?
So we can just plot the qualitative
that's good enough.
Plots,
Yes.
and that
Yes.
should be
Don't
enough.
worry about the stability analysis. Okay.
Okay.
Any other doubts, questions?
Do we have to show a kind of null line in this case?
How will you do null line in a 3D world? You can in principle, it's going to be very hard. No? But if you can collapse that into just two axes, maybe yeah, you can.
So can we take two derivative as 0 at the same time? And
yeah, it just may, don't worry too much about it. So I'm not expecting a lot of algebra, work here. Huh? I wanted to think more and do less algebra. Algebra must be fairly basic. So just to the extent of finding equilibrium. Okay, I think stability should be able to intuitively argue out what's going to happen. Okay. Okay, is it fine? Shall I open the breakout rooms again? Yeah.
Yeah, about the half saturation constant, given that they're both using the same resource, I'm not sure I completely understand whether they will sort of be dependent on each other or not.
Okay. I mean, so they may depend. So of course, the real world is complex and I can imagine some interactions happening there, right? You can make an assumption that they're independent.
Okay.
Sir?
Yeah.
Like, when is the submission for this?
How about tonight work, or do you want up tomorrow afternoon?
Tomorrow afternoon would work if it's
Is
possible.
preferable. Okay. Yeah. So tomorrow afternoon. Okay, fine. Yeah. 2 p.m. I can keep it at 2 p.m. tomorrow afternoon.
So to reiterate, we just need to find the equilibria
and then the conditions for it, and then interpret those. Okay.
Okay, sir. Okay.
Even if you verbally argue stability, it's good enough.
Okay, sir.
No
Fine.
need to mathematically do the Jacobian matrix. That's going to be a huge messy affair.
Okay, sir.
Okay, cool. So I will open the breakout rooms. Some of you said you need to leave at 4, but that's fine. But I hope that most of you will still be around, and I'll visit you again at around 4:30. Yeah, I've opened the breakout rooms.